Hey, this is Dr. B here, and in this slide we are going to solve a real calorimetry problem, and you'll see that it's not the usual yada yada. And then we'll actually consider a more generic way of solving enthalpy problems by looking at standard enthalpy of formation. Let's dive right into this problem. You got 50 grams of a metal, it's at 115 degrees Celsius. So maybe they placed it in some hot oil at 115 degrees C until that rock, turned to that temperature. Then they stuck it in a fully insulated cup, sometimes known as a cheap calorimeter, and that has 125 grams of water in it at 25 degrees Celsius. So you're taking a very hot rock and you're putting it in water. Somewhere in this problem, it should have said that there's no heat loss, but let's just assume that's so. And it's not going to be, it's just a styrofoam cup, but it's okay. Pretend there's no heat loss at all. And the water's at about room temperature, maybe slightly warmer. It goes up by about 4 degrees. We should be able to use that to identify the metal. So maybe we can just plug into Q equals mc delta T and we've got ourselves a solution. But no, it's not that simple. I can remember trying to solve these earlier as a chemistry teacher and saying, "Ooh, what the heck is going on here?" There's two things going on, right? The metal is going to heat up the water, right? All of the heat that was lost by the metal is absorbed by the water. So let's go ahead and solve the problem. We're going to find the heat that's gained by the water. So deal only with water first, and you might find out that that works out nicely. You can solve that. In fact, if you really want to do this, you can just plug into Q equals mc delta T, and you start getting confused because you got water, you got rock. It's like, what do we have? And then once we know that that value, that amount of heat that was gained by the water, that must be equal to the heat that was lost by the metal, we can now go back and solve for the specific heat of the metal. Check it out. When you're writing your Q values here, I recommend that you always write some subscripts like W for water or M for metal. The heat that was gained by the water is equal to the mass of the water. We know that, right? What is it? 125 grams times the specific heat of the water. We know that too. It's liquid water, 4.184 joules per gram degree Celsius, times its temperature change. What did we say? A little under 4 degrees. And there it is. Plug that all in and we're going to find how much energy was gained by the water. 1900 joules. Fine. Now the big transfer. Any heat that was gained by the water had to come from that hot metal, right? So that is also the heat that was lost by the metal. Now finally the formula for the metal only has one unknown, right? The heat that was lost by the metal, which is 1900 joules, must be equal to the mass of the metal, which we have, times the specific heat of the metal, which we're going to solve for, and it's going to match something, times the temperature change of the metal. We know that, but can you see which one it is? It started at 115 degrees. We have two numbers here. Which one do we use? Well, it clearly didn't go down to 25.6. It went down to 29.3. The high temperature of the water is also the low temperature of the metal. I hope that's clear. So that'll be our delta T. Oh boy, we're close, right? There's our numbers. Where are we? M, Q, yeah, we can rearrange it. I would rearrange. Oh, I think I did. C equals Q over M delta T. There's our Q, there's our M, there's our delta T. We get a number of 0.44 joules per gram degree Celsius. It's a moment of truth when you do this because whenever you do this, make sure you get a number less than about 4. Otherwise, you're dealing, basically nothing has a specific heat higher than water. It's 0.44, which is a nice match for iron. It looks like they probably took a chunk of iron. That is a real-life calorimetry problem. Another way to solve sort of enthalpy problems is by dealing with what's known as standard enthalpy of formation. Incredibly powerful tool. And hopefully by the time I run through this, you'll agree. So let's define the standard enthalpy of formation of any element in its most stable form as 0, right? So the enthalpy of formation of oxygen is plain old 0. Here's another thing, it looks like it only has oxygen in it. But it has to be the most stable form of that element. Add that to this little definition here if you need to. So ozone is not zero. See that? Another little thing that students mess up sometimes is carbon. This is the same thing. Oxygen versus ozone. This actually is, these are not allotropes. These are different substances. These are truly allotropes, different forms of pure elements. And so it has to be the elements in their most stable form. It turns out that graphite is zero, but diamond is not. So watch out for those, okay? Just because you have an element, you got to be in the most stable form. That's fine. So if you're doing any chemical reaction, now hopefully you'll see the true utility of this. Any chemical reaction, you want to find out the heat of the reaction, it's just equal to the sum of the products minus the reactants. So you look up this substance, you look up this substance, and then you subtract out that substance and that substance. Watch out for the coefficients. If you have more of it, you simply multiply it. Does that make sense? Because this formula is really, juju. It's just nuts, right? The standard enthalpy change of a reaction at standard conditions is equal to the sum of the molar change in the enthalpy of the formation of products minus reactants. There's so many symbols here that it messes you up. But if you just think about it, it's just products minus reactants. You look them up in a table. But then I hope you have that aha that it's like, you mean this works for anything? And, I think as long as you got your data, it probably does. So you can come up with just all sorts of chemical reactions, how much heat should be given off or required without performing them. So a very powerful tool. This is calorimetry and standard enthalpy of formation.